Welcome everyone to the residence time distribution practicum intro video. Process engineers develop methods to make or purify products in small or industrial scales. Everyday examples comprise beer brewing, water purification plants, or simply making a nice pasta at home. As you can imagine, when you want to make a nice al dente pasta at home like the Italian, or making a nice bitter beer, it is important to know how long the compounds will stay in the pot or the fermentation tank. This is what we call residence time. As you can imagine, depending on the reactor, the residence times will be different.
In the case of a batch reactor, for example, which you can think of as a pasta cooking pot, the residence time will be from the time you put the pasta in the pot until you remove it when it's cooked through. But if you have a continuous process where you have constant input and output, the residence time will be more difficult to calculate.
Oh, but if you have the volume of the reaction and you know the volumetric flow rate, you can so easily calculate it.
One can imagine deriving the residence time by simply taking the ratio of those two, but as you will see in today's experiment, the residence time will depend on the type of the reactor, where you have maybe different mixing regimes or events like channeling, or simply the existence of dead zones, which will render the reactor far from ideal. In today's video and experiment, we hope to be able to explore these concepts more in detail.
Okay, so in the introduction we saw why we might want to think about caring for the residence time distribution or calculating a residence time distribution for a real reactor system. And so just to reemphasize why we should care about this. So on one side, we need to think about the length of time that reactants spend in the reactor influences reaction rates and product quality. And also, if we think about our job as process engineers is often to scale up a reaction, we want to think about matching this residence time from the lab scale to the production scale. And so if we can think about calculating things like a mean residence time, which we will define as tau. And as one of our students pointed out, we can think about this often as just being the volume of the reactor over the volumetric flow rate in a very simple way. But life is always not so ideal, and we need to do a bit more calculations to see if this holds for all systems. And also, this only gives us the average residence time, and sometimes we want to think about the residence time distribution, which we'll define as a function E of t, which gives us the amount of time that each unit mass of a reactant spends in the reactor. So we get a probability distribution for how long reactants spend in our reactor. And so if we start thinking about some real reactor systems, two of the common continuous reactors that we use we can think of as pots or pipes. And so the pot reactor we can think of as a continuously stirred tank reactor, or a CSTR. And so in this system we just have a large tank that's under mixing with an inlet stream and an outlet stream. And our main assumption in the CSTR is that we have perfect mixing in the volume of the reactor, such that we have the dispersion or the effective diffusion coefficient of reactants in the system tending towards infinity. So we add reactants in, they mix perfectly and instantaneously. Another type of reactor that we can think of is the plug flow reactor. Or a PFR. And so in this case, we also have a continuously operating system, but it's in a pipe. Again, with an inlet and an outlet, but instead of having perfect mixing in this system, we make the assumption of having no axial dispersion. And so if we define a coordinate axis x, this is the same as saying that the dispersion in the x direction, or the diffusion coefficient in the x direction, tends towards 0. And so in both of these systems, if we think about adding a mass element of reactants into our reactor, we can think about what might be the expected concentration of that mass element coming out. And so when we have perfect mixing in our CSTR, we might imagine that this mass element gets mixed instantaneously in our reactor. And if we start to quantify the amount of concentration at the outlet stream, we could expect that it's going to be high at the initial state upon perfect mixing, and then it's going to slowly decay as we have mass flowing out of the system, or liquid flowing out. In the other case of the plug flow reactor, if we add a plug of mass into the system, this is going to just travel down our reactor as a perfect plug with no axial dispersion. And so we can think of the expected concentration that would come out as just a pulse of concentration that is delayed by the time that one would expect from the volume of our pipe and the volumetric flow rate of the system. And so these are quite simple cases, and we can actually do some simple math that will show at the end of this video to calculate things like the expected concentration profile for the CSTR, and we'll also deal with the PFR in the experiment. But in real life, we have not always perfect ideal CSTRs or PFRs, and we have real reactors. And so let's just think of a very generic black box reactor that is still operating continuously. So we have an inlet stream and an outlet stream. And again, we add a pulse of reactants into this system. Now, if we don't know what is happening in the system, we may have no idea what to expect for how the concentration of that pulse that we add in would come out at the other end. But let's say we can measure the outlet concentration and we can get some distribution like this. Now, it may be more difficult now to think about what is the mean resonance time and what is the resonance time distribution for this system. And so this is why we've thought about these definitions of having tau as an average resonance time or E of t as a resonance time distribution. And if we know our concentration profile at the outlet stream, we can calculate this E of t just by converting this concentration profile as a function of time into a probability distribution. And so this means that we can just take our concentration at a given time divided by the total concentration that comes out. So if we just integrate over all time of this concentration profile and we take every instantaneous concentration that comes out, we can turn this into a probability distribution, and this is by definition our resonance time distribution. So it's saying that for each element that comes out, we can say how much of the mass that we added in came out and how long did it spend in the reactor. From this, we can then calculate a mean residence time by taking the first moment of this probability distribution function. And so this just means that we average, or we find the average time for this probability distribution. So this is the same as integrating over all time for the time times the concentration over this normalized concentration. And so this would then allow us to have now both the residence time distribution and a mean residence time for our new reactor system. And so when we're actually designing reactors, we want to think about how can we actually go about doing this. So one way is we could certainly do some trial and error. And we could set up a lot of tests in our system, trying to understand if we design it this way and we add products in, how much reactants do we get, and try and map this back to a residence time distribution. But this is quite costly, and it takes a lot of personnel to do so. Another way is that we could think about modeling the system. And so if we have a good idea of how the reactor looks, maybe we could use computational fluid dynamics or other systems. But this can be challenging because we don't know if there's dead zones or parts of the reactor that are not getting accessed by fluid, or channeling, so parts where fluid flows faster than we expect through the reactor. And so this doesn't always relate back to the real condition that we have. And so for this, and what we'll see in the experiment that we've designed to show you today, we can actually think about using tracers as a model reactant that we can add into our reactor as a pulse, just like we showed here in the theoretical case. So we can add a pulse into our reactor, and then if we design it correctly such that we can then measure this concentration at the outlet, we can start to think about how we can calculate our residence time distribution as well as the mean residence time.
As you saw in the last part, when thinking about processes, we are interested in quantifying the residence time distribution of the particles in the reactor. We looked at how small mass elements passing through the system change over time. And in order to quantify the residence time distribution of the system, we need to be able to track and measure these small mass elements. But how do we do this experimentally? Well, we can use a tracer experiment where we modified one of the properties of the fluid and measure this property. For example, we can measure the concentration of a non-reactive substance in the fluid. This substance, which is known as the tracer, needs to have similar characteristics as the fluid. In addition, the tracer needs to be easy to measure and quantifiable. For example, we can use color to track changes in the system. In the Practicum, we will introduce methylene blue at the inlet of the reactor, which will change the color of the reactor over time. However, this is not easily quantifiable. Therefore, we will also measure the electrical conductivity of the fluid, which will tell us the concentration of potassium chloride. This is a very quantifiable method and will allow us to perform a tracer experiment to calculate the residence time distribution of our reactors. To measure the electrical conductivity and hence the concentration of potassium chloride, we use parallel electrodes as the measuring system. Here, we apply a voltage and measure the electrical current. Because potassium chloride dissolves into positively and negatively charged ions, dissolving different amounts of potassium chloride in the fluid will change the conductivity of the fluid. And the current that we will measure is proportional to the concentration of ions in the fluid. Therefore, if we can measure the electrical conductivity of the fluid after adding known amounts of potassium chloride tracer, we can construct a calibration curve, which will enable us to determine the concentration of tracer just by measuring the electrical conductivity of the fluid in the reactor. So now we have seen what kind of tracers we're going to use, and we have seen how to measure these tracers and quantify the concentration of tracers in the reactors over time. But the question still remains, how do we administer the tracer? One can imagine that we can inject the tracer in a continuous manner. However, several problems remain because the concentration of tracer will be constant at the inlet and the outlet over time if administered in a continuous manner. Therefore, we should administer the tracer in a stepwise manner or a pulse-like manner. In our practicum, we will inject the potassium chloride and methylene blue in a pulse-like manner. Ideally, the distribution should look like a Dirac function, where all the tracer is administered at one time. In practice, the distribution will look more like a Gaussian curve. After the tracer injection, we will measure the tracer concentration over time at the outlet of the system. And this will allow us to experimentally calculate the residence time distribution of the particles in our reactor.
We have seen how it is possible to measure residence time distribution experimentally, and together we're going to test this on multiple real setups. But first, it is interesting to understand what we should actually expect for our experiments. So let's take the example of a pulse injection in a CSTR. So a CSTR is basically a vessel, and one of the important assumptions is that this is perfectly mixed. So as it is a continuous system, we usually have an inlet and an outlet. So to describe these two streams, we use the volumetric flow rate at the inlet, the volumetric flow rate at the outlet, as well as the concentration at the inlet and the concentration at the outlet. So one of the before actually your arrival at the experimental facility, we will also going to fill up the vessels until we reach a steady state. For this reason, we can say that the volumetric flow rate at the outlet will be the same as the volumetric flow rate at the inlet, which will be the same as V dot. And also, our experiments will be a pulse injection. So what we're going to do is we're going to inject the tracer, in this case is potassium chloride, at a specific time point, which we call t equals to 0. So now if you want to describe the variables of the inlet and outlet streams, what we can say is actually the following. So first of all, before we start, the important thing is also to describe two new variables, which are the volume, which is the volume inside the CSTR, and also the concentration, which represents the concentration inside the CSTR. So let's now look at the streams. So at t greater than 0, what we can actually say is that the concentration of tracer in the inlet is going to be 0 because we do a pulse injection. Also, if we look at t equal or greater than 0, we can also say that the concentration at the outlet of the CSTR will be exactly the same as the concentration inside the CSTR. This is thanks to our assumption of perfectly mixed vessel. So now, if we would like to understand how does the concentration evolve inside the CSTR. And for this, what we can actually think is that at t equals 0, the concentration inside our CSTR will be equal to the concentration that is given by the pulse injection. In this case, we call it C0. And this is nothing else than the mass of tracer that we have injected divided by the volume, total volume of the CSTR. And this can also be expressed by the concentration of tracer times the specific volume of tracer that we add divided by the total volume of the CSTR. However, what we would like to predict is also the concentration at t greater than 0, because this is the original question that we had. But in order to understand how the concentration evolves at t greater than 0, we need actually to calculate how does the mass evolve over time inside the CSTR. And to do this in chemical and process engineering, we do a calculation which is called the mass balance. In this case, we do the mass balance at t greater than 0 because we know what happens at t equals 0. So this means that we would like to know how much mass of tracer is accumulated in our reactor over time. And for this reason, we write this accumulation term. And this is equal to the mass of tracer which is flowing inside our reactor minus the mass of tracer which is flowing outside of our reactor, plus there is also another term which is called the production term, and this accounts for the mass of tracer which is generated or consumed inside our system due to chemical or biological processes. So as we are doing this mass balance for t greater than 0, actually we know that there is no tracer which is flowing in, and also we do have no chemical and no biological processes, and therefore there is also the production term is also 0. So we are left with a very simple relationship, and this can describe the evolution of the mass over time. So our accumulation term can be rewritten as the change of mass over time, and this is equal to the mass flow rate which is flowing outwards of our system. So, but in order to continue, we need to write these two quantities in known quantities. For instance, the concentration and the volume. For this reason, we can rewrite the mass of tracer as the concentration of tracer times the volume of the CSTR divided by differential of time, and this can be also rewritten as the concentration of tracer times the volumetric flow rate at the outlet, which is equal to the general volumetric flow rate because we are in a steady state. And now we can rearrange this equation. By multiplying with dt and by dividing both sides with the concentration and also by dividing both sides with the volume. Why? Because the volume is constant and can be taken out by from the differential. So what we are left with is the differential of the concentration divided by the concentration of tracer, and this is equal to dt over the volume divided by the volumetric flow rate. But if you think about it, and if we remember from what we have known previously, is that this term here is nothing else than the ideal mean residence time. So now we can rewrite this equation as dc over c, and this is equal to minus dt over tau. And given what you have seen before, we can actually use these quantities here as our boundary conditions. So we would like to actually integrate this equation from a time point which is 0, t0, from a time point which is So we would like to integrate this equation from a time point which is T0, where the initial concentration inside the vessel is C0, up to a general time point T, where the concentration inside the vessel is general C of T. And if we integrate this relationship by a separation of variables, we actually are left with a natural logarithm of C of T over C0, which is equal to minus T over tau. And then we can write this in our final an important relationship, which is that we can describe that describes the evolution of the concentration in the CSTR over time, where which is given by C0, which is the initial concentration, times the exponential of minus T over tau. And this very simple equation that we have derived analytically can describe the evolution of the concentration inside our CSTR, given the fact that we have done a pulse injection and that the reactor is perfectly mixed.
So we hope we convinced you that residence time distribution is an important concept in process engineering, which allows us to design and monitor reactors.
Now that you have an insight on how to determine residence time distribution, it is important to put those skills into practice. So we are all looking forward to see you during the practicum, and we hope you enjoyed this video. Cheers!
Cheers!
Cheers! Cheers!
Can I have a beer as well?
Of course!
Of course!
Cheers!
What a nice residence time.